Yes, Ashish. Now you say what's the question.
Sir, can we calculate this ripple theoretically as we did for sine triangle PWM?
We are doing theoretically. We are computing the time intervals, right? Tz by 2, and then again T1, and then T2, and then Tz by 2. We know the error voltage vector. What is the magnitude? Its magnitude is Vs. What is the inductor? We know. What is the time? We know Tz by 2. So we know what length it is traveling here.
Okay, sir.
Okay.
Yes, sir. Yes, sir.
Similarly, here also we know the magnitude. We know what is the error voltage magnitude is basically V1 minus Vs. The magnitude of V1 minus Vs.
Yes, sir.
So of course we are doing the exact computation. It's not just analytical, like it's not just qualitative.
Okay, sir.
Understanding my point? These points we are computing. I am drawing just approximately for your understanding first. But the exact points, what we are reaching, this can be computed in the similar manner, how we have done for the sine triangle. So you need to know the intervals which we are aware about, Tz by 2, T1, Tz by 2, and T2. And we know what is the magnitude of this vector, what we are applying. So please mind that this is the shape of the ripple only at 30 degree. If you go for 10 degree or some other angle, the shape will be different slightly. Okay, it may have little longer on one side, and then for D axis maybe little longer, and then it may come back. You understand the point here?
Yes, sir.
Yes, sir.
Okay. Now, same thing. So this understanding we have got, right? How we are getting the D axis and Q axis ripple, right? This point is clear. So for 0, 1 to 7, what we are finding that we are getting this kind of ripple in our system. Now, say if we take another vector sequence, let's say 7210. Say we are taking that, and again we do the analysis in DQ domain. Okay, everybody I think aware about the DQ domain, right? There is no problem in that. We'll discuss more about this when we are discussing machine, but as of now just assume that it is as per whatever you have studied in your previous classes. And maybe I'll copy this so I need not draw this again and again. Okay, now we are considering a vector sequence which is basically 7210. Our voltage vector, same voltage vector, say of this much height located at 30 degree is shown over here, Vs. Now when we start 7210, what we will do, we will apply 7 first. But the nature of voltage error is same. It is basically negative of Vs. Then we apply 2. So which means this error is applied first. And then we apply this error. And then we apply the 0. So what will happen to this ripple over here is that, see, this is positive Q axis, this is positive D axis. Now here what will happen? Of course, for the application of 0 vector, this will move along the Q axis only. But now, because you are applying this vector first, so it will move along the positive side, sorry, on the negative side of D axis, something like this. It will be flipped. It will be just whatever we have drawn, the flipped version of that. And then when you apply vector 1, this is the error. So again, it will move parallel to that and it will come back to this position and then it will move back to origin. This will be corresponding to 7210. Magnitudes are exactly same, only it is flipped. So what is effect on D and Q axis? 4 intervals we can draw. And then we have applied the 0 vector 7, so it moves along the negative and then it goes to positive and some more positive and then it comes back to 0. So more or less the q-axis ripple remains same. There is no problem in that. The d-axis ripple, now it is going towards the minus d once you start the active vector 2. So now it will look like this. So peak to peak for d-axis will come from 0, 1 to 7 and then 7 to 1, 0. So this is negative peak, that is positive peak. So like that you can see. Understand my point?
Yes, sir.
Fine. So these numbers you should be able to compute. If I ask you to draw, you will have to compute these numbers on basis of similar computation what we have done for sine triangle PWM. Okay. Am I fine here for everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now
Yes.
let us do the same exercise for the special sequence, say bus clamping PWM. Now what do we have? We have 0, 1, 2. That's all. So what we are doing, we are applying this 0 vector 0 for duration of tz. We are applying 1 for time period t1, 2 for time period t2. And we have the vector located at the same location, say here, and magnitude is also same. So error caused by the 0 vector 0 is basically opposite of that. And the error vector caused by vector 1 is again similar to what we have seen for the conventional space vector PWM. For 2 also it is similar. Exactly same actually. So what will happen to the ripple? Now we are applying the 0 vector 0 for whole duration of tz, which means it will go in this direction continuously for the complete duration tz, large negative value. And then we are applying the vector 1. So it's coming back because if you move parallel to this, it is coming back. And then it is going something. So maybe it won't cross for this particular condition. It will remain up to slightly negative. And then because this is coming parallel, so it will something join like this at the origin. So this will happen with 0, 1, 2 alone. So q-axis ripple is completely on only one side, similar to d-axis ripple. So if you draw the q-axis current ripple, what is happening now? It's going large negative value. And there are only 3 intervals. So we need not bother about the 4th one. So it's going for large negative value. Then it is coming back to some slightly negative portion and then moving almost parallel to this and going to 0. This is the change in q-axis ripple. T remains the same because for 0 it won't move. For again 1 it will move to some positive value and then for 2 it will come back to the same position, which is 0. So now you see that the peak value of q-axis ripple has gone double of that almost, right? Or actually double of that. So which means the peak to peak ripple on q-axis current has doubled. It's going on one direction only. So RMS is also going to increase significantly. And that's why for bus clamping PWM, say for example 0, 1, 2, we see large RMS value for the current ripple. The harmonic performance is poor for bus clamping PWM. The reason is this: your q-axis current ripple has become very, very poor compared to the conventional. You understand my point?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, on the same graph, let us say, if I apply some advanced bus clamping, we have talked about something like 1012. On the same graph, because comparative study is needed over here. So what is happening? My 1 is divided in 2 parts. So I have to make 4 splits in this itself. So let's say I'm drawing the boundary here for the TZ. Fine. So, and one boundary is say here. Error due to vector 1. So which means it will move, but only for a duration of t1 by 2. Understanding my point? Fine.
Yes, sir.
Fine for everyone, or some disturbance happened?
Sir, there was some disturbance, sir.
That's what I also felt. Okay, so what I'm saying that now the intervals are different. Earlier there were the red boundaries, which are these are giving the intervals for 0, 1, 2. Now we have the first vector getting split in two parts, t1 by 2, t1 by 2, and 0 vector tz is coming in between the two, and then vector t2. Correct? This is what we are trying to have. Now we are applying 1, 0, 1, 2. So first is we are applying the vector 1, which means the error is due to this vector which I am indicating here. So corresponding to that, my current error will move parallel to that, but only for a duration of t1 by 2, not the full duration t1. Then after that I am going to the 0 vector, which is 0. So which means the error is corresponding to this arrow, this vector. So then it moves parallel to that. You understand this?
Yes, sir.
Okay. Again, I am applying vector 1. So again, it moves in this direction. Say up to this point. Not completely crossing the Q axis, this thing. Up to this point, it has come. And then I have vector 2 applied over here. So 1, 0, and then again 1, and then 2. That's what I have applied. Now see the difference yourself. Earlier we had for 0, 1, 2, the ripple was so big. It is visible here itself. And now for this advanced bus clamping 1, 0, 1, 2, it has become so small. We always talk about the peak-to-peak ripple or RMS ripple. So if you see the Q-axis peak-to-peak ripple, you have some positive value going due to the vector 1, and then you have coming to the negative side due to the vector 0, say something like this. And then again, you are applying vector 1, which is taking very, very close to 0, almost up to this point, and then it is coming here. You see how the peak-to-peak ripple has reduced significantly for advanced bus clamping PWM. D will have the same height, but little bit in the distributed manner. So for vector 1, it will go on the positive side. Okay, I had drawn here. Actually, it should have been like this on the positive D side. So first, for the sequence 1, 0, 1, 2, the ripple on the D axis will move slightly positive. Then we are applying 0. So no change on the D. So it will remain flat. Then again, it will move and meet the same height. And from there, it will come back to 0. So D axis peak to peak remains almost same. Shape is slightly different. Whereas Q axis, if you see, it has significantly changed. That's the reason why we go for advanced bus clamping. This improves our current ripple as well, apart from giving the bus clamping in the particular phase. But we have come back to the same switching frequency. So advantage of bus clamping is that our particular phase is not switching, which means the switching loss corresponding to that phase has reduced. So here we are not switching our B phase. So corresponding to B phase, our loss has reduced. And we are doing the bus clamping at a particular place where our current ripple is more. So we are kind of distributing the loss or kind of having more switching where our current is lower. So in effect, we will have lower switching loss for all three phases actually, while also reducing our peak to peak current ripple. So that's the advantage of advanced bus clamping PWM. If you go further, if you are not bothered about how many switchings we are having, say 10, 10, 12, what you will have further smaller sections going like this: 1 and then 0, then 1, then 0, then 1, then this 1 and then 2. So it may become further smaller. So similarly, you can analyze the current ripple for any such sequence, any sequence which you wish to make. But there has to be some advantage. Of course, here we have more switchings, but the response is that we are clamping first of all, and then we are having lower peak to peak ripple.
Sir, for D it is maximum, sir. For 10, 10, 12, I think, sir.
D will remain almost same, right? Because D is dependent on only active vectors. So anyway, you are applying the active vectors for total duration T1 and total duration T2. So it will move, then stop, then move, then stop, then move, then stop. Ultimately, it will have the same peak. This height on the D will remain same for all three. Although here I have not drawn it properly, but this height on the D will have the same height. You understand my point?
Yes, sir.
Yes, sir.
Okay. If you draw with proper time durations with the scale and know this thing, you will find that D is not changing in terms of peak to peak ripple. Shape may be different. There may be more steps within D, but the peak to peak value will remain same. Whereas Q will have several zero crossings like this. So that is how we are minimizing the ripple. We are making it go across the zero axis multiple times. If you allow it to go along one side completely and then come back to zero, that's large ripple. If you keep switching between the plus minus values, this is basically a smaller ripple. Understanding my point?
Yes.
So now you can do the analysis for the current ripple for any sequence, right? Correct?
Yes, sir.
Why everybody is not saying yes? Still you have doubts?
No, sir. Yes, sir.
No, sir.
Ajay?
Sir, I haven't gone through the previous lecture completely, so what
No, little louder, Ajay, please.
I haven't gone the previous lecture complete. I haven't completed the previous one lecture.
Okay. Revise that and then try to do it on your own. Sampan? Fine for you?
Yes, sir.
Saurav, Uday Kumar, Sukumar? Fine for everyone?
Yes, sir.
Sir, one question was there, sir.
Hmm.
Sir, it means while we are going to reduce the switching losses for any particular sequence, we are inherently increasing the current ripple, no?
If you go for conventional bus clamping, if you go for any bus clamping which is 60-degree clamp or 30-degree clamp, which is the conventional sine triangle way, you are bound to increase the current ripple.
Oh, yes.
There is no other option. But if you go for space vector based techniques, which is like advanced bus clamping, difficult to realize on triangular carrier based PWM, that is giving advantage on both fronts. It is reducing your switching losses as well as reducing your current ripple.
Sir, in general, like which one we give preference, like reducing
yes.
the switching losses overall
Or reducing the current ripple, sir.
The best way is having sinusoidal current and sinusoidal voltage, which is having zero switching and zero losses also. But as close as possible we could be. If we can have all, take everything. But if you cannot have all the things, you prioritize. What is your first priority? If your system can sustain so much of current ripple, fine, go with that. Have the minimum value of the switching losses. And if your system can take so much of switching losses, you can go for reduction of the current ripple. It's up to your system.
Yes, sir.
Yes,
Okay.
sir. Yes.
Sir, for an example, sir, for a high power density motor drive, so our main focus should be the switching losses should be reduced. Ripple we
This is
can
the catch actually. What happens by having switching losses? We are talking about the losses in the converter, right? And by having lesser ripple, that means harmonic losses, we are talking about losses in the motor. If your converter is well designed, you can have so much of switching losses. You try to reduce the losses in the motor, which means your ripple or harmonic. Understand my point? These two things are separate. If you are sure that your motor can take so much of ripple, then you try to minimize the switching loss, because then your converter size will reduce. These are options. For integrated motor drive, we have both the things mounted on the same assembly. Then for us, the best thing would be to have some common point for both. Don't have too much of losses in the motor, don't have too much losses in the converter as well. Some common ground we need to have. Understand my point?
yes, sir.
Yes, sir. Yes, sir.
So two losses are occurring at different places. The switching loss or conduction loss is something related to the converter, power converter. Harmonic loss is something related to the motor or the ripple or anything, whatever we talk about the current. So it depends. If you have very robust motor, go for converter improvement. If you have very robust converter, go for motor improvement. Integrated needs to have both. Okay? Fine?
Yes, sir.
Yes, sir.
Yes, sir.
So in a way, our Q-axis current ripple is giving us the minimum value of current ripple. That is fine. That is one thing. But current ripple is also associated with something which we have seen in the low switching frequency PWM as harmonic, but here we are going to see as ripple. So ripple on the torque. So harmonic, when we say, it is particular harmonic sinusoidal component which is varying at 6th or 12th or 18th, like that. But ripple is something which is like combination of all the harmonics, sum of all the harmonics. So this ripple is basically very much dictated by what is the ripple on the Q-axis current. General way to understand is that, say, how is torque produced? Torque is produced by interaction of flux and current. Now we know that our DC flux is associated along the D-axis flux. Sorry, along the D-axis. The DC flux or the flux is lying along the D-axis, this we know. So this, when you take the cross product and all, this is going to interact with the Q-axis current to produce the DC torque. Understand my point? So if you have any ripple on the Q-axis current, that will also interact with the DC torque on the D-axis, DC flux on the D-axis, and that will result into the torque ripple. That's the reason why we are more concerned about Q-axis current ripple, again, when we try to minimize the torque ripple. Sine triangle doesn't say anything about torque ripple. It says, okay, you minimize the current ripple, torque ripple will also improve. But here we have specific understanding about the torque ripple, that it is dependent on Q-axis current largely. So if you have any PWM technique, for example, say bus clamping and advanced bus clamping PWM, these two techniques, if you want to compare 012 and 1012, which one will have better torque ripple? Which one will have?
So,
All of you are
1012.
1012.
1012, because this is resulting into lower value of Q axis current ripple.
Yes.
So this is not only giving the improvement in terms of current ripple, but also in terms of torque ripple. There may be some techniques which may result into almost similar current ripple if you combine D and Q axis, but they may give significant reduction in torque ripple. So we can design our PWM in a manner what we want. If we want to have reduction in current ripple, try to have in this manner. If you want particularly if you want to have a reduction particularly in the torque ripple, you can design in that manner as well. Understanding my point?
Yes, sir.
So any PWM, let's say you take whether it's this low switching frequency or sine triangle or any special space vector PWM, any such technique you can analyze in terms of this method. And then you can see which one is advantageous, which one is not. Of course, when you are going for low switching frequency, this will not be the exact way of doing, because that will not be based on sample. No, it's the complete waveform. So there we will have to draw it in a little bit different manner. That I'm not discussing in this course. So that is also a way to do the analysis, but we can do from a space vector point of view. And of course, any triangular carrier based method, whether third harmonic injected or bus clamping or any other PWM technique, you can analyze in this form and you can see what advantage you are getting in that. Correct?
Yes.
So a quick derivation, let us see for the torque ripple what I was saying, and then we will go for some couple of examples and then we close the class. So couple of ways we have seen to derive the torque. Here is another method. When you go by the vector components, let us say if I talk about current vector in the DQ domain, it will have component like ISD plus JISQ. More details we will come on this. We will discuss on this a little bit in the vector control side and all. And flux vector, if you talk about, again in the DQ domain, we have two components, PSI-SD and PSI-SQ. Correct? So torque, we know that is basically the cross product of flux vector and the current vector. This can also be written as imaginary component of torque and current conjugate. The product of torque and current conjugate is simple. When we are taking in this form, there is no theta, there is no this sine delta kind of thing. Here we are talking about the components. Then these two things are exactly same. We will derive this in the coming classes. We will derive and prove that this is same. So this is where we have another way of deriving our torque. So then we can write K times of, and this is imaginary component only of what? Of PSI-SD plus J PSI-SQ and the current conjugate, which means ISD minus JISQ. The imaginary part of this product between these two, component wise product. So what will come out? Only what is associated with the imaginary number, the J. So here we have PSI-SQ, ISD, minus we will have PSI-SD, ISQ. That's all, right?
Yes, sir.
Correct. So this is the torque expression if you talk about DQ domain. We will prove this point later when we discuss in the machines. Now, once we have this expression, we know that when we are going for DQ domain and all that, what happens to the sinusoidal quantity in DQ domain? How does it appear? It appears like a DC.
DC quantity, yes.
Correct? That's the general understanding. And what happens to the harmonics? Harmonics will remain harmonics. Correct? So whatever ripple you have in the stationary reference frame, that will look like a ripple only in the synchronously revolving DQ reference frame. Correct? So in effect, what may happen that any of the quantity, let's say we talk about flux or current or anything, will have basically two components in the DQ domain. One will be a DC component, one will be a ripple component. Correct, right?
Yes, sir.
So any quantity will look like a DC and then some harmonic sitting on this. So then we can write, what we can write? We can write our flux, let us say psi is D. This can have two components, psi is D0 plus psi is D ripple. Then psi is Q will have psi is Q0 plus psi is Q ripple. ISD will have ISD0 plus ISD ripple. Then ISQ will have ISQ0 plus ISQ ripple. These will be the components of these quantities as DC and the ripple part. So you can plug these quantities in this equation. And what you will find is that torque, now this I am writing as combined torque. Okay, don't confuse, this is only ripple, this is combined torque, DC plus the ripple. So psi SQ becomes psi SQ0 plus psi SQ ripple multiplied by ISD, which is ISD0 plus ISD ripple, minus the D-axis flux psi SD0 and psi SD ripple, and ISQ0 and ISQ ripple. This is correct, right? All four components we have written. Ajay?
Yes, sir.
Now, important thing to notice over here is that the Q-axis flux is 0. We don't have DC flux along the Q-axis. It is only located along the D-axis. Correct? And if we talk about the condition where motor is operating at no load, to simplify the things, nothing else, then Q-axis current will also be 0, DC current. We are not drawing any active power. Something maybe for the losses or and all these things, friction windage losses and this resistance losses. Only these small component of Q-axis will be there. But largely we can take that as 0 for now. So we have only these remaining components, which are basically K times of. So psi SQ will get multiplied to ISD0 psi SQ plus psi SQ and ISD ripple minus psi SD0 ISQ ripple and psi SD ripple and ISQ ripple. These four components will come out, right? Correct?
Yes,
Now,
sir.
we have seen in the previous class also that product of ripple with another ripple is very, very small number. Something which is very small, you are multiplying with another small quantity. So product can be regarded as 0, can be taken as 0 with respect to the other quantities which are having significant magnitude. Now, this torque, okay, so we have removed this Q-axis current, so we don't have DC torque now because it's running at no load. So this is only ripple torque. The moment you say no load, this is basically no DC torque is there. We are only talking about the ripple torque. So the components remaining are ISD0 psi SQ ripple minus psi SD0 and ISQ ripple. Now, when we have high switching frequency case, this Q-axis flux is basically L into ISQ. These two are related basically, ISQ and psi SQ. So the ripple in the flux can be written as ISD0 minus psi SD0 divided by, or we can perhaps multiply L over here, L times of ISD 0 and then psi SD 0 times of ISQ ripple. So don't say that L into ISD 0 is psi SD 0. That's not the case. Okay, this we are talking about leakage only. Here the magnetizing inductance will be involved for this computation. So in effect, what is happening, our torque ripple is coming proportional to only ISQ and no other quantity, ISQ ripple. And which is why we say that the reduction in torque ripple is straight away means that you must reduce your Q axis current ripple. Q axis current ripple alone, not bothered about the D axis current ripple. Okay, for the no load case we are talking about. So general understanding is this: if you want to reduce your torque ripple, reduce the Q axis current ripple. So there are few techniques in a space vector PWM which particularly focus on reduction of the torque ripple through reduction of the Q axis current ripple. Understand my point?
Yes, sir.
Yes.
So this is how we correlate our torque with the quantity which we have seen over here, which is the Q axis current ripple. Any doubts up to this point?
So this is for the no load case, sir.
Yes. For full load case or any other load case, you will have to include ISQ as well. So then the psi SD ripple will come into picture. Okay.
Okay, sir. Okay, sir.
We are taking a simpler case where, okay, if we are able to reduce the no load ripple, fine, we are happy. Understanding my point?
Yes, sir.
So this almost completes our space vector PWM, unless you have any other doubts. So I think I have covered most of the things, whatever I had to teach in this course regarding space vector PWM. Some quick example we can see regarding the current vector and how the ripple looks like. So this is what I have tried to plot over here. You see, the ripple what I am talking about is basically, this is how the current vector is moving. It's not moving on the circle. The red circle what you see over here is how the fundamental current vector would move. It would move on the circle. Whereas your ripple will take this path, which is going in zigzag manner around this average value, around this circle. Understanding my point? So this triangle or something what we were drawing, assuming that this is at a fixed position, basically this is moving slightly. So this will also get shifted. No, this will also get twisted. And that is what you are seeing over here. The twisted form of those triangles. This is conventional space vector PWM. So somewhere around this point we have tried to draw our current ripple, and so you see it looks like a triangle. No, it's going in that fashion only, moving in one direction and then going for 1, then 2, and then 7. So coming back to the same circle, starting from the circle, coming back to the circle. Understand my point?
Yes, sir.
Okay.
Yes, sir.
If you just want to visualize how it is, so assume that any kid is there who has just pulled this towards the negative D axis. Okay, is just dragging it towards the negative D axis. So this will remain same. It will come back to the D axis, the origin or this on the D axis, but it will be shifted little bit. Let's say this will be moving little bit on the negative D side. That's all what we have here. This is for a case of good pulse number. So if I change the pulse number, the things will look different. Here I have done for pulse number which is very high, something like 63. Pulse number 9, if you want to have, this is how it will look like. So big ripples, right? Because we have time durations which are very, very large. And this is exact reflection of how your current ripple on the actual current is looking like. This is the reflection of the same thing. Whether you analyze from the per phase basis or analyze from this, the result will be same. Correct? This we are doing for conventional space vector PWM. Now, same thing, if you try to increase the pulse number, it will improve. Let us say you talk about pulse number 15, it will of course improve. See here. As this ripple is improving, this is also coming closer to the circle. So which is what I tried to do for very high pulse number like 63. So then it's like almost closer to the circle. So we are dealing with inverter states. That is the meaning of inverter state. We do not get a perfectly rotating current vector or a perfect circle for the tip of the current vector. We get some zigzag path around that. So on an average, this is going in the circle. So techniques like DTC, what they do, they try to force this current vector or tip of the current vector to, or the flux vector to move towards this circle every time. So instead of, if you have one applied vector, then you can think about another vector which will take it closer to the circle. Then you go close to the circle, you cross it, and then again you come back to the circle by applying the other vector. So in effect, we are only trying to have somewhere close to this circle and we are rotating. That is all is the PWM. Fine.
Yes, sir. Yes, sir.
Okay. So let us stop the class over here. And I hope that now things are clearer to you.